Welcome back to our series on statistical methods. I'm Mark Ledbetter. This is Lecture 29, Part A, and we are discussing regression, and this is Part 3 of Chapter 10. Now, in the last video, we derived and showed that the expected value of beta 1 hat was equal to beta 1, which means that it's an unbiased estimator for beta 1. Now, in this video, we're going to start with the variance. Remember that the MSE of beta 1 hat would be equal to the variance of beta 1 hat plus the bias of beta 1 hat quantity squared. Since the bias is zero, because these two values are the same, then the MSE of beta 1 hat is simply the variance of beta 1 hat. So let's go ahead and get started. We take the variance of this lovely equation. Remember that this is a constant. And what happens to the variance of constants times something is that we square that constant. So we get this. And then we use the same trick as we used before, distributing these two quantities. And remember that when I take the y bar times the sum of xi minus x bar, that's 0. So that term cancels out. I'm just left with the first term with yi in it. And so I end up with the sum of xi minus x bar times the variance of yi. This has an I in it, so again, I can't get rid of it in this term that's circled here. That does not go to 0 because each value is multiplied by the variance of yi. For each value, I get the square. It's not of the whole sum, but when I take the variance, I had the sum of the variance of xi minus x bar times yi. This part is a constant, so it gets squared. So I need to correct my notes here slightly, and this is a square. Okay, so then one of those cancels out with the with this square on the bottom. Okay, and so we end up with the variance of yi over the sum of the squares of x, and so we can use either the symbol sigma squared or s sub y given x squared. And we call this whole thing s sub beta 1 hat squared. Don't forget the hat, because beta 1 is a constant and there is no variance or deviation associated with it, so it doesn't have a variance. Its variance would be 0. But the estimate is a statistic, and statistics do have distributions, so they would have a variance. It turns out from what we've learned, we should know beta 1 hat minus beta 1 divided by s sub beta 1 hat is a t distribution with n minus 2 degrees of freedom. So we can now use our formula for a confidence interval for beta 1, which is beta 1 hat plus or minus t n minus 2, and should not be 1 minus alpha 2. I'm sorry, it should just be alpha 2. This is t n minus 2 alpha over 2 s sub b 1 beta 1 hat. We can do hypothesis tests for this. In fact, there's 3 of them. The null hypothesis is always the same, that beta 1 is equal to some beta 1 naught, some value, versus it's greater than, less than, or not equal to. Okay? And the t statistic, or test statistic, t naught, is again beta 1 minus beta 1 naught, whatever the value is we're testing against, divided by its standard deviation. Okay? Or standard error. Okay. Rejection criteria is, again, I've written these as a different book has them, so I need to correct the notation. That would just be alpha, and this would be alpha over 2. So we've got the t n minus 2, the degrees of freedom for our SSE, and alpha. So alpha, for the one-sided we have alpha, and for the two-sided we have alpha over 2. Okay. Now let's talk about the sampling distribution of beta naught. The expected value of beta naught is the expected value. We fill in its value here. And so we can remember that the y's are the only things that we have. This is an expectation with respect to, let me get rid of the red here, with respect to y. Okay. So this term is just a constant, and it's going to follow through as just a constant. But to find the expected value of y bar, it's easy to break that up as 1 over n times the sum of yi. The 1 over n is a constant, so it comes out to the front, and so we have the expected value of the sum, which is the sum of the expected values, and we can rewrite that as the regression line, and then we solve and we end up with the fact that the expected value of beta naught is equal to beta naught, so it is an unbiased estimate. Then we have the variance of beta naught. So we take the variance of this, and again, it's with respect to y because x is a constant. So this is a constant, and so this becomes 0. And the covariance of a constant with a variable is 0 as well. And so we're left with the variance of this first term, and we can, actually, I'm sorry, it's not a constant because beta 1 hat has a variance. Okay, so I'm sorry that this is not 0 for the reason that I thought. So we're left with this variance, and it's because beta 1 hat has, it is a random quantity. But x bar is a constant, so we treat it as a constant. It comes out as the square, x bar square, which is what we see here. Okay? But the covariance is 0. You can work this out, but basically these terms cancel out, but I will leave that to you. But it is a 0. It's a little tedious to show, so I won't force you to go through that, but just know that you could work it out. With what you've learned in this class in Stat 333, you could certainly prove this if you keep your quantity straight and no careless errors. Okay, but it is unbiased, which is good. Now, so the variance turns out to be, if we solve this, 1 over n squared times n, so this n and this cancels, sigma squared, plus x bar sigma squared over the sum of the x's, xi minus x bar squared. We can factor out the sigma squared from both terms, and we end up with this expression. So this is the expression. I don't expect you to memorize it at all, of course. Even if we were having tests, I wouldn't expect you to know the equation. But if we were doing tests, you might have to derive this, but we're not doing tests, so you're safe. All right, so then I can rewrite sigma squared with its alternate notation, if you like. And again, note that beta naught hat minus beta naught over its standard deviation has a t distribution with n minus 2 degrees of freedom. So it's nice that both of these have n minus 2 degrees of freedom, which is the degrees of freedom of the sum of squares error, SSE. Okay. And so again, I've written this. I've copied this from a book that uses a different notation than us. So that should be t n minus 2 alpha over 2 s sub beta naught hat. So that's our formula for the confidence interval for beta. So the hypothesis tests, they're going to be exactly the same as beta 1 hat, except substitute beta naught hat in there. They're exactly the same. So let's talk about the interpretations of a test for zero slope. In other words, beta 1 is equal to 0. So we're always interested in testing if beta 1 is equal to 0, because if beta 1 is equal to 0, then it's saying that x will not help predict y using the straight line model. Okay, so if the slope is 0, then we basically have, if beta 1 equals 0, then y is equal to beta naught, which is a straight line, which is constant. And so that would say that it's not dependent on x, so we don't have a relationship or an association between x and y if beta 1 is 0. So we're always interested in testing this hypothesis. And if we fail to reject h naught, so in other words, if beta 1 can be said to be 0, then we have either x does not help to predict y, or the true relationship between x and y is not linear. It could be quadratic, cubic, exponential, log, square root, what have you. But it wouldn't be a straight line. If we do reject h naught, then we'd say that x provides significant information about y, and there still could be a better model than linear. So here's some examples of when beta naught is equal to 0 is not rejected. So if it's not rejected, then that means that we can assume that the slope is 0. And so if we have this, then there is no association. But here we could fit a best line that is quadratic through this, but the best straight line that's fit through this would still be y is equal to a constant, some constant, beta naught. Okay? But there is an association here. It's just not linear. So again, this points us to the importance of graphing our data. Plotting the data is very, very important, so that if we don't just blindly look at a p-value and the results of a test. Okay? All right. And then we have a couple of examples of when we do reject h naught, beta 1 equals 0. And we have in the first graph, we have a fairly straight line relationship here, positive in this case. Here we're fitting a straight line, but the best line would be something different, maybe a rotated parabola. Okay? In the next lecture, we will talk about doing some inference about the mean and about individual points on the regression line. All right, that's it for this video. If you have questions, please make sure you come to virtual office hours. If you need help prior to office hours, by all means email me. But when you email me, if it's about a problem, then email me what the problem is, because I may not have it available, and then your work on that problem so far. If it's code, then by all means send me a copy of the code, and in the email tell me where you're having the problem and that you need help. And I will get back to you as soon as it's possible. Please take care of yourself and stay safe, because we want to see you here next time.